Tutte's theorem. Tutte's theorem. A graph G has a perfect matching, if and only if, the number of odd components of G minus S, is at most the number of the elements of S, for every subset S of V. We shall refer to this condition as Tutte's condition. Suppose that G has a perfect matching M, and let S be any subset of the vertex set of G. Then, for any odd component K of G minus S, there must be at least one edge of M in the cut associated with K. As K is a component of G minus S, every edge in this cut has one end in K and one end in S. We deduce that the number of odd components of G minus S is smaller than or equal to the number of the elements of S. Summarizing, we have that, if G has a perfect matching, then Tutte's condition holds. Conversely, suppose that G is a graph that has no perfect matchings. We shall show, by induction on the order of G, that G has a subset S of V, for which the number of odd components of G minus S is greater than the number of the elements of S. We shall refer to such a set as a Tutte set. If G has an odd number of vertices, then the empty set is a Tutte set. We may thus assume that G has an even number of vertices. For a subset S of V, we define the deficiency of S, denoted by Fs, as the difference between the number of odd components of G minus S and the cardinality of S. Clearly, a subset of positive deficiency is a Tutte set. Denote by Cs the total number of vertices in the components of G minus S with no perfect matching. For example, consider G as the Sylvester graph, and the set S of one vertex, depicted in the figure below. The graph G minus S has three components, each one containing 5 vertices. Thus, in this case, we have that the deficiency of S is 2. And Cs is 15. We now introduce the most important object of this proof. It is the set S, which will be proved to be a Tutte set of G. Among the subsets of V with maximum deficiency, consider a set S, such that Cs is minimum. The deficiency of a set with just one vertex is 0 or more. It follows that the deficiency of S is 0 or more. We shall show that, in fact, the deficiency of S is strictly positive. That is, S is a Tutte set. We first show that every even component of G minus S has a perfect matching. Suppose that K is an even component of G minus S, with no perfect matching. Let V be any vertex in K. Let S' denote the set S, plus V. Then, every odd component of G minus S is also an odd component of G minus S'. Moreover, the even component K of G minus S contains one or more odd components of G minus S'. Then, the deficiency of S' is at least the deficiency of S, while Cs' is smaller than Cs. This contradicts the choice of S. Thus, every even component of G minus S has a perfect matching. The second property we are going to show is the following: let K be an odd component of G minus S. And let V be a vertex of K. Then, K minus V has a perfect matching. Suppose that K is an odd component of G minus S, and that K minus V has no perfect matching. By induction, K minus V has a Tutte set T. Since K minus V has cardinality even, the deficiency of T is at least 2, in K minus V. Let S prime be the set formed by the union of S, T, and V. Since every component of K minus V minus T is also a component of G minus S prime, we have that the deficiency of S prime is at least the deficiency of S, while CS prime is smaller than CS. This contradicts the choice of S. Thus, this second property also holds. Let H be the bipartite graph, obtained from G, by deleting the vertices of the even components of G minus S, contracting each odd component to a single vertex, and deleting the edges spanned by S. Then S is a part of the bipartition of H. Denote the other part by T. Let M be a maximum matching of H. Let us show that M covers S. Suppose that M does not cover S. Let X be the subset of vertices of S, not covered by M. Let Z be the set of vertices of H minus X, that can be reached from a vertex of X, by an M alternating path. Then every vertex of S intersection Z, is joined by an edge of M, to a vertex in T intersection Z. Moreover, by the maximality of M, no edge joins a vertex in S intersection Z to a vertex in T minus Z. Let S prime be the set formed by S minus S intersection Z. Using the two properties of the components of G minus S we have proved, it follows that the vertices of S intersection Z, plus the odd components that are joined to them, by the edges of M, form a set of vertices of G which has a perfect matching. This set, added by the possible even components of G minus S, that are joined to S intersection Z, form an even component of G minus S prime, which has a perfect matching. It follows that, the deficiency of S prime equals the deficiency of S, while CS prime is smaller than CS. This contradicts the choice of S. Thus, M covers S. We have seen that the deficiency of S is non-negative. If the deficiency of S is 0, then G would have a perfect matching. We conclude that the deficiency of S is strictly positive. Thus, S is a Tutte set.